Hello, sir.
Sorry? Okay, I'm just checking the internet once. Sometimes it causes a trouble. So, hi.
Sir, are you saying something? I think you're on mute.
I'm not on mute. Are you not able to hear me?
I can't hear you. If you're saying something.
Just a second.
So you will speak once more?
Can you hear me now?
Yeah, now I can hear you.
Okay, so there's some lag. Okay. There's a little lag, but hopefully it shouldn't be a problem.
Okay.
Okay. Is it clear now?
Yeah.
Okay. Perfect. So quickly tell me a little. So by the way, I'm Atray. I'm Atray Sir's brother, and I teach physics and chemistry.
All right.
For 11th as well as 9th and 10th. So my background as such has been in IT in the past, but now I focus more majorly on physics and chemistry only. Okay, so because they are the building blocks at the end of the day of any technical field. So tell me a little bit about yourself and what's been going on in school also, what chapters you're on, how did you do in the previous classes?
This is an older book, but if I go according to this, let's see. We have done oscillation and waves. Right now sorry?
Completed it?
Yeah, we've not completed it. We have done oscillations. We've done sound waves, and we are basically focusing on diffraction. We did diffraction, and today we were on resolution.
Okay, and is this the first chapter?
No, this is not the first chapter. This is the chapter we are currently on.
Okay, so what all have been done earlier, previously?
We have done measurements and uncertainties. We have done mechanics. We have done thermal physics. We have finished oscillation and waves, and we are on wave phenomena.
Okay, fine. So quite a lot of the major chunks have been done already. Okay. And I mean, what do you have chemistry also, or just physics and maths?
No, I just have physics and math HL.
Okay, fine. Okay. So perfect. So let's start with oscillation for today, and the other chapters we'll come to them as and when we get the time. Okay. So tell me quickly about, I mean, since you are studying it already, what have you understood about oscillations and simple harmonic motion so far?
I mean, so far, simple harmonic motion, we've understood that it's a restoring force. Its movement, it turns the potential. It has like points, right? At a certain point, when it has the maximum velocity, it'll have the most kinetic energy. When it's stationary at one of the ends, it has the highest potential energy. And I mean, yeah, it's been some time since we did that chapter, but yeah.
Okay, so I'm not going to jump into waves directly because waves require you to understand the oscillations first, right? So, I mean, I never jump onto a bigger chapter where the fundamentals are not clear. That's essentially what both me and Atray Sir teach, that your fundamentals should be crystal clear so that everything else builds upon each other. Okay? So we'll be starting with oscillations. So it might be a little repetitive, but you'll see that how interesting it can be once you start understanding the concepts. So oscillations, first of all, is quite simply an object which moves to and fro. Okay, but that to and fro motion happens from a mean position. Okay,
All right.
so when this mean position, so this can be zero, whatever. So this is another important thing. It doesn't always have to be zero. Okay, a lot of people get confused in that. So suppose if I make a Cartesian plane, I do not need to always have the oscillation around this point. Okay, I can also have the oscillation around this point, and it's the same thing at the end of the day. I can also have the oscillation around this point. Now, the position of the point is irrelevant till the time my criteria for oscillation is there, which is to and fro movement around a mean point. Okay, so we take origin usually as a mean because that's the most convenient one. Okay, it does not mean that it's the only one. Now, so there are a lot of terms that come into play in oscillation. First is periodic motion. Any idea what that is?
I mean, it repeats a specific motion in a certain amount of time.
So how is this different from oscillation?
I mean, okay. I mean, oscillation would be a repeated movement, and oscillation specifically, you said, is about a mean position to and fro, whereas, like you said, a periodic motion, it doesn't have to be, it just has to repeat, that motion should be repeated.
Good,
It doesn't have
very
to be
good.
to and fro. I think that's the difference.
Nice, correct. So you've already understood the first aspect of our teaching, which is we try to teach thinking to students. Okay, a lot of people just will give you the definitions and it'll be done in like 2 classes, but you wouldn't understand because right now when you thought about it, I'm pretty sure you wouldn't forget the difference. Okay, I'm here to clarify those doubts, but once you've thought about it, once you've understood the difference, it's very difficult for you to forget them. Okay, so periodic motion and oscillatory motion are essentially sets and subsets of each other. So periodic motion essentially is a motion, recurring motion, which is, as you said, recurring in a fixed period of time. A classic example of this is rotation or revolution. None of them are oscillatory, but they are definitely periodic, right? And a swing of pendulum is also. So swing of pendulum is also a periodic motion because it fulfills the criteria of recurring in a fixed period of time. Now, oscillatory, on the other hand, as we've already understood, is to and fro motion around a mean in a fixed period of time. And this example will be the same here. So this will be applicable here as well. And of course, the spring action or the vibration of the guitar, all of these will also be fulfilled. Okay, that means what? That if this is my periodic motion, if this is the set of periodic motion, then oscillatory motion is a subset. Okay, so every oscillatory motion is a periodic motion, but not every periodic motion has to be oscillatory motion.
Understood.
Okay, so that is the basic difference between these two. And now there is a difference between, is there a difference between oscillation and vibration? Any idea?
Oscillation and vibration. From what I've gathered, both are movements, yes, about a mean position, and yes, to and fro. Um, yeah, I'm not sure about this one.
Yeah, so they are not different. Okay, both of them are same. Okay, now
Okay.
I'm telling you this because a lot of the question, a lot of time in questions, they might be used interchangeably. Okay, sometimes they use oscillation, sometimes they use vibration, and people get confused. But there is no difference between oscillation or vibration. Okay, it's
Okay.
just that it's basically two different terms talking about the same thing. But in general, when we use it, we use oscillation when the frequency is very less. Okay,
Okay.
do you understand that? Suppose if I start moving my hand up and down, now is this oscillatory movement? Yes,
Yes.
correct. But the frequency is really less. Okay, it's probably like one in 1 second, right?
Hmm.
One uh, movement in 1 second. So I will call it oscillation. But if I increase the frequency, say for a string of a guitar, when I increase the when I pluck it, the frequency is crazy. It's probably like 100 times in a second,
Hmm.
right? And that's when I just call it vibration. So it's essentially the same, but when the frequency is less, we call it oscillation. When the frequency is more, we call it vibration.
Keep.
Okay. Again, these little details. So in science, any science, okay, almost 70% of the time, if you want to answer a question, 70% of the work is done just by understanding what the question is asking.
Okay.
Okay, and if you notice it when you practice the questions in our class or in the previous classes, you'll notice this is true, because if you've understood a question properly, then you know what is being asked and you can answer it really quickly. Okay, a lot of
Hmm.
times people get confused. Hey, what does this mean? What does that mean? I don't understand what's going on, right? And that's where the confusion comes in. So that's the key thing in science. The language becomes really important. Now let's move on to simple harmonic motion. Simple harmonic motion is the simplest form of oscillatory motion. Okay, it's the simplest form of oscillatory motion, and essentially, uh, we say a periodic sinusoidal motion. Okay, so again, when we talk about oscillatory motion, the motion can be in different ways. It can be this way, it can be and so on. Okay, but okay, so this will actually go down, my fault. So technically, these are also
Oscillation.
oscillatory motions,
Hmm.
right? Makes sense, right? They are happening around a mean position. But the problem with this, or we still call them oscillatory motion, but they are not simple harmonic. For harmonic motion, our graph would be of a sinusoidal wave. Now, what is a sinusoidal wave? Have you heard of
Yes,
it?
I'm familiar with the sine graph. Yes.
Where does it come from?
Trigonometry.
Yes. Okay. What are the examples where we see it in physics?
Well, simple harmonic motion.
No, simple harmonic motion is the name that we've given, but what are the natural phenomena where we see it?
Oh, I suppose, well, graphing the movement of a pendulum, or I don't know, less dense object going up and down in water.
Yes. So a lot of ways we also see it in waves as well. Okay. So the AC current is essentially a sinusoidal wave, right?
Mhm.
Almost all the electromagnetic waves are sinusoidal waves, right? You must have done it in 10th.
Yeah, we did that, and we also like using bridge rectifiers. You would remove everything below the x-axis. So yeah, we are familiar with that.
Yes. Okay. So sinusoidal wave is a really important aspect of physics. And in nature also you see it in a lot of ways as the examples that you gave. Okay. So the pendulum is a perfect example for us to check this. Actually, we've come across the first wave or kind of the trace was the easiest one to do it from a pendulum. Okay. And from then it is kind of taken forward. Now there are a lot of different aspects of this: amplitude, um, wavelength, time period. What are they? Do you have
Well,
any idea?
yes. Well, the amplitude is the highest or the lowest. It's either the crest or the trough.
Yes. Okay. What
Uh,
else?
the wavelength is the, well, how far the wave travels for the in a the time period.
How far the wave is traveling in a time period,
Yes,
correct? What
that's
else? What is
how
the frequency? Okay,
frequency
so
is. Yeah,
just
yeah.
just as a side note, I'll be using frequency as this. Okay, so I'll be using this notation, but in your book, at times I think it's given as F itself. Okay,
Yes.
so I can, okay, just to simplify it, I'll also use F only. Let's make it, keep it easy. Okay, so I'll keep it as F, but in case somehow if I use this, uh, either correct me at that point or just like remember the difference.
Okay.
Okay, so it's essentially the same thing. Again, we are just using two different variables
Hmm.
because I've used more V, new as we call it. So this has been in the practice. Okay, so in
Okay.
case I make a mistake around it. Okay, so what is frequency?
Well, how many times that movement happens in given time period,
How
or
many
how
times
many?
that, yeah, say that again. How many times that movement happens in a given time period? Are you sure?
Or, well, no, but unit time, not the time period. Unit time per second.
Yes. Okay. So the difference between time period and F is essentially time period is the total amount of time to complete an oscillation.
Hmm.
Okay. It is the total amount of time to complete one single oscillation. And the distance that is moved in it is the wavelength,
Okay.
right? The frequency is the number of vibrations per unit time. Okay,
Hmm.
these are definitions, and the better you understand the definitions, the more accurate your understanding will be. Okay, so frequency is number of times the vibration happens per unit time.
Hmm.
Okay, and that unit can be anything. It can be seconds, it can be days, it can be hours, it can be months, it can be years as well.
Yeah.
Okay, so our revolution happens once per year. That is the frequency of it.
Hmm.
Okay, our rotation happens once per day. That is the frequency of it. Okay, a string that vibrates at 100 or has 100 vibrations per second.
Hmm.
That means 100 times it is going up and down per second. Okay, so that is frequency. Um, simple harmonic motion can be now described into this form. This is essentially the sinusoidal form. We can either use cos or we can also use omega t. Okay, they are again interchangeable. There's not much difference. Okay, if I add a pi here, it'll be the same thing. Okay,
Yeah, it's
so
just a displaced sine graph, right?
yeah, it's just a display sign graph. If I start from 0, then I will use a sine. If I
Hmm.
start from 90 like this,
Hmm.
okay, then pi by 2, which is called in radians, then I will be using a cos. Okay, so we
Okay.
can use either of them depending on where they are. A more general form of this is like this. This is the most general form.
Okay.
What are these? What is omega? What is this is called phi. So what is phi?
So the if I just take the first equation, A, I'm guessing yes, it's the amplitude. The phi is,
Why are you
well,
guessing?
well, not guessing. I mean,
Uh,
it's just, yeah, it's written there. So yes.
okay.
Um, Phi. Okay, so phi is the angle you drop it from, right? Or the angle you the displace. How? What angle it started from?
Okay.
And omega t. Omega, as far as I remember, is the angular frequency.
What is angular frequency? So I'm both trying to quiz you and teach you at the same time. Okay, it's very easy for me to kind of just jump into it, but I want to understand how much you have comprehended from your school classes and uh, at what level are you
Very
at.
little from the school classes.
So where are you saying all of these things from then?
So these are things I remember, and whatever is coming from intuition um, and familiarity. Because like in class, whatever happens. It's always a rush.
Okay.
But
Okay. So in class, you haven't really understood this properly.
no, I'm not comfortable with it.
Okay. Hmm. Interesting then. Like that means you are quite smart in putting in context. Okay, that means even though you don't know what each of them are, you're still trying to understand what they might be, which is really nice. Okay, that's a really good quality. Okay, so let's break them piece by piece. A is very simply the amplitude. Now, before we talk about amplitude, amplitude in our case is essentially a form of displacement, right? But when we talk about displacement in mechanics, right, it has a very specific meaning, which is the uh, shortest distance between 2 points, irrespective of what all motion they've done. Okay, so the shortest distance and the direction from initial to final. But here in oscillation or even in in waves, we take displacement in a more general form. That means the displacement here, when we use the word displacement here, we're not just talking about the direction and the initial final positions. We are actually talking about the position in general, the position parameter in
Mhm.
general. Okay. Now that position parameter can be of any physical quantity. Let me explain. For example, when we talk about pendulum, one way to think is that the pendulum moves like this, right? So either we kind of take the distance from initial to final and then go from there. But a better way is to just take the angle, okay? To just take the angle and then understand how this angle changes per time. Okay, over time, how is this angle changing? And that becomes our displacement. So for pendulum, okay, so by the way, this is as any physical quantity changing according to time, because the time component is very important. For a block plus spring model, there is no angle. In that case, it is the proper displacement as we know it. I'll use distance here, or a better word would be position. Okay, again, these are from the main position. So the main position for this angle would be here, which is my vertical line. And from there, I'm taking the angle. And similarly, for mean position of block plus string would be the 0 or the whatever the center is. And from there, I'm taking the position.
All right.
Okay. So it can be different for different things. So like in the case of AC voltage or AC current, there is also a sinusoidal wave, and the physical quantity over there is voltage. Okay, we are not talking about any position, we are not talking about any angle, but voltage. And yet that voltage would be put under displacement. Okay, so we are taking that voltage as a form of displacement. Okay, again, I'm telling you all of this because you shouldn't get confused between mechanics and simple harmonic or oscillations in general. Okay, because the word used is the same. Right? Because if we don't understand the words correctly, then we are only half learning the things.
Okay.
Right? So once we've understood displacement, now we can go back to amplitude. Amplitude is the maximum value of that displacement. Whatever displacement we are using in that particular scenario, okay? Amplitude is the maximum positions of that displacement, or simply we can just say maximum displacement, and that was also sufficient. So now it could be max voltage, max distance, max angle, and so on. Right? Next comes frequency, or let's go for omega. Omega is the angular frequency. Now let's understand this. Let's use this, and we have A cos omega t plus, let's skip out phi, so that because we are trying to derive what omega is first, okay, and then we'll come back to it. So let's say this is case 1. Now I want to see what happens. So the time period of this would be how much?
Well, t, right?
Let's say it's t, although
not the small t.
Sorry?
It's not the small t.
No, it's not the small t. Okay, let's. Now I want to see what happens when it repeats. So when it repeats, we know that A cos omega t will be equal to A cos omega t plus the time period. Yes? Time, that's what time period means, right? When the time after the time period, that is one rotation, one oscillation is complete, the quantities will be the same. Correct?
Okay.
You look confused.
I mean, I'm just trying to soak it all in.
Okay.
So here you've basically you're saying the small t is 0, and for the time period, for that certain time.
No. I never said the small t is 0. Okay, so first understand what this is. This is a function. Okay, and you must have done it in maths. If it's a function, this is the distance parameter. That means what is the position of whatever I'm checking, say the block, with
Yes.
respect to time. As the time is changing, how is the position of that body changing, right? So when my time changes with a fixed omega, and I'm trying to find out what is the value of omega, so it is kind of a variable for us as well. So the time is variable, but it changes according to us, right? But this whole function, we already know that it has a time period t, whatever that time period may be. Okay, I do not care about the magnitude, but I know that this function will repeat itself once after one oscillation. That means
Okay, I understand.
my time elapsed is t plus capital T.
Okay, I understand now.
You understand now? Sure?
Yes.
Okay. So this is recurring after a specific time. So we know that this will be true. Now, for cosine or even for sine, the period, not the time period here, the period of repetition is 2 pi. Are you familiar with this?
Yeah, 2 pi is 360 degrees.
Yeah, 2 pi is 360 degrees. And essentially, when we make that diagram, okay, the sine, when we make a diagram of cos theta or sine theta, essentially what is happening, the graph keeps on repeating itself after every 360 degrees,
Yeah.
or 2 pi. Okay, this is in radians, by the way.
Yes.
Right. If you don't understand anything, please tell me so that I don't assume that you already know. Okay. So essentially what is happening, we know that cos as a function itself. Okay, so cos theta as a function has a period of 2 pi. We already know that, right? Now, we are already seeing that here, this and this are getting equal. So this implies that omega t plus t should be equal to omega t plus 2 pi. Is this step clear? This is the most important step to understand.
So the x-axis, while we're graphing currently displacement as time goes by, you can also define it in terms of displacement as you cover a certain angle.
No, we're not talking about the angle here right now. Okay, understand. I'll make the diagram so that it's better understood for you. See, what's happening is, say I take start here. Now, if I start at 0, this is my time. This is my time period. What is happening? The value here is the same value as here. Is that right?
Yes.
Right? And this is a cos omega t. The sinusoidal wave is a depiction, a graphical representation of a cos omega t. Now, a cos omega t, the value of a cos omega t is exactly the same as a cos omega t plus capital T. So now, at every point after this t, the values will be exactly the same.
Right.
Right? Any point. I can take any point, and the values will be exactly the same after this time period. Okay. So essentially what I've done, I've replaced t in omega t with t plus capital T here. Okay, that's how you replace things in a function, right? Now, at the same time, we already know the period of cos theta. We already know the period of cos theta from mathematics, which is 2 pi. That every 360 degrees, every 360 degrees, the graph repeats itself from trigonometry. Yes? So that gives us the period of cos theta as 2 pi. Now, if this were to be true, essentially what this means is omega t should only repeat after 2 pi. Therefore, this value should be equal to omega t plus 2 pi. This is the minimum.
Okay.
Did you get it now?
Yeah, I think so.
Still unclear.
No, so like what I said in the beginning, when you said you should probably draw the graph and explain to me, what I simply meant was the time period, which is the x-axis currently, or time, my bad, and the oscillation, which is the crest, the trough, and the crest again, repeats every t, capital T. I understand that.
Yes.
And the capital T corresponds to 2 pi.
No, the capital T doesn't correspond. We are trying to find that relationship right now. Okay. So I'm not saying that capital T is equal to 2 pi.
No, I'm not saying that either. I'm simply saying it corresponds to it in the sense, just like it's repeating every T.
Yes. Yes, correct. So they are corresponding in a sense, but here we are only talking about the theta aspect of it.
Okay.
When we make the graph of cos theta or sin theta, right? We did not take the x-axis for us is not t. It is not dependent on time, right? We take angles, like after what angle. So if I were to make the same graph, but now for cos theta, my x-axis, my y-axis will be the displacement or the amplitude. Displacement is the right word. Displacement. And here, this would not be t because there is no, it doesn't matter on t, right? What is the variable here? It is theta. Right? So my theta keeps on changing. So if I start with 0, it will be say pi by 2, then we'll reach pi, then we'll reach 3 pi by 2, then we'll reach 2 pi, and then we'll reach 2 pi by 2. Oh, sorry.
2 pi, yeah.
2 pi plus pi by 2, and so on. This is exactly what happens. And here we notice for cos theta, that it repeats after 2 pi.
Okay.
Right? So now we are trying to overlap them. Okay, hey, we already know that for cos theta, the period is 2 pi. We already know this, right? That means if I take theta here, and if I take 2 pi plus theta here, that means cos theta will be equal to cos of 2 pi plus theta.
You get the same amplitude or displacement.
Yeah, we get the same values. We get the same magnitude, right? So with this knowledge, we are trying to apply here, where this is the value that we have for time period. Now we are using time period of the wave. Okay, this is the value that I know that the vibration is going to repeat after a particular amount of time, not theta, time. Okay, this is the option of the wave. And for cos theta to repeat, we already know that this theta,
right,
plus 2 pi should be the same,
Yep, this I
right?
understand.
Because
Yep.
cos theta is only going to repeat after 2 pi.
Yep.
Did you understand it now?
Yes.
Okay. So once we have this relationship, now we will be able to find what exactly omega is. So once we have this, now we can quickly simplify it, which is so omega comes out as 2 pi upon capital T.
All right. So yeah,
Understood?
I get this. Yes, I
Okay.
get this.
Which is also the same as, because 1 upon T, 1 upon capital T is also what?
Frequency.
Frequency. So I can also write this as 2 pi f.
Okay.
So omega, the angular, this is the angular frequency. The angular frequency becomes, this is the relationship I have with angular frequency and time period, or the frequency. Okay, the general wave frequency. Okay, that means what? जो भी हमारा frequency था. Now understand, what was frequency at the end of the day? What was frequency
Well,
at the end of the
how
day?
many times, like vibrations per unit time?
Yes. How many times the vibration is happening per unit time? So suppose this is one wave and I make another wave like this.
Yeah, so this one has a much higher frequency.
This one has a much higher frequency. And so but it is quite possible that the angular frequency may be the same. Okay, no, it won't be the same, but the angular frequency changes with the frequency. So that's why we have this relationship.
Okay.
Okay, and the angular frequency is just how fast is the angle changing. Okay, the angle, because the angle is essentially, this angle is essentially what gives us the position.
Hey, the slope is much steeper. It's covering much more angle in less time.
Yes,
Of the
that's
graph.
exactly what this is. Cos theta tells us the slope only, right? This is what it tells us. That's why we are making it. Okay. So this is a really important derivation, and it's important because this gives us a really good relationship between frequency and time period and omega. Okay. So angular frequency also means how
Angle covered per second, or whatever your unit of time is.
yes. So when we are talking about angle as a displacement, okay. When we're talking about angle as a displacement, that's when we are using this term. Okay, so if I take a pendulum, and this is one point and this is another point, how fast is the angle changing?
Right.
Okay, how fast is the angle changing, and how is that related to my frequency here? Okay, so because when I calculate the time period, I'm trying to calculate what? This time period, which is from one extreme to the next and then back. This will be my time period. Yes, that will be
Yep.
my one oscillation. So when I have the time period, how quickly is my angle changing? So
Right.
how minutely, how quickly is my angle changing? And that is what I am trying to find out with angular frequency.
Okay.
Right? Because it will be very difficult for me to otherwise find out. Take care. Is this clear?
Yes, it's clear.
Perfect. So, okay. Just a second. Let me check how much time we have. Okay, the units for angular frequency are what?
Well, I'm guessing it should be radians per second.
Correct. They are radians per second. Okay. Now, let's see what kind of graphs can be made. So, we've understood A, we've understood omega. The only thing remaining is phi. What could be phi?
Yeah, so phi should be like if there is a, normally you would assume it starts at the center line or what you have deemed as the mean position. And if you displace it with a certain angle from the beginning, sorry, I'm guessing that would be phi.
Correct. So, essentially, where are we? This is called phase, by the way. It's called phase.
Okay.
Okay, phase constant, to be precise. The whole thing is called phase. Okay, this is the phase constant because we are starting with this, and this whole thing is phase. And this will again be used again and again. An interference that you're doing, interference simply works. The whole concept of interference works on phase. Okay, do you know how this works? Do you know what phase is exactly?
So
how it's relevant?
If you like took well, because when two waves, I'm guessing they come into contact with each other, there's a resultant, right? There's a change. I'm guessing the graphs are displaced. Each point is added to each other in the graph is added to it.
So why this is relevant to interferences? Interference essentially means when two waves come together, okay, what happens? That is exactly what interference is. Now, if two waves of the same phase come in, okay, and phase, right, like you said, essentially means from what point? This is the phase constant. From what point or from what angle am I starting? So if my phase constant is this, then this becomes my wave. And so on. Okay. And my time period will be taken from here. This will be my time period. Get it?
Yep.
Now, if I have another wave of the same phase, but a greater amplitude, an interference between them happens, then they both get added up. Right. Okay, they both get added up because they're happening at the same phase. Okay, but if the phase was negative, that means if I started here, if the phase was negative, so I start exactly at minus phi, like this.
It would completely cancel out.
It will completely cancel out. Correct. Okay.
So that is adding each point to each other, right? You're just adding each point to each other.
Yes. I mean, see, it's not that simple. When we come to interference, we'll understand it in detail. But right now, I'm just trying to explain why phase is important. Okay. Here, because I've made it like this, that each point, because the phase is starting point are the same and the frequency is the same. Okay. Only two things are important here, which is the starting point, which is the phase should be the same, and the frequency are the same. Then each point get added up. So the resultant of these two will be the amplitude of this plus the amplitude of this. Okay, so I cannot make it because it'll be out of the board. But the resultant of this will be amplitude of this plus the amplitude of this. So it'll be really big. So it'll go really high. Okay, and here was amplitude of this minus the amplitude of this.
Yeah.
Okay, so it becomes 0. It cancels out, right? But if the frequency is different, then it changes. Okay, or if the phase is different, then they get added up in a different form. Okay, so that's what that we'll do when
Yeah,
we
I can
come
see
back.
it getting very tricky. Yes.
Yeah, so it becomes, I mean, so basically once we understand this, once we have this formula, this form, now we can simply add it mathematically and we'll have the interference also. Okay, so if I have a cos phi plus theta, and I get another wave as well, say b sine uh, theta, omega t plus phi dash. Okay, suppose I
Okay.
have another wave and I need to find the interference. I just add them mathematically first. Okay, so I try to get an expression like this in a mathematical form, and then I depict that onto graphically. So interference
Yeah, that
becomes very
would be
simple in that
much
sense.
easier. Yeah.
Okay,
Becomes easy.
but to
Yes.
do it graphically becomes very difficult when there are a lot of other variables.
Yep.
So coming back to phase becomes important. Phase tells us basically where, at what point it is starting, and what is essentially uh, how it's going to be progressing. Okay, so at what point it's starting. So it could be this, it could be this, and so on. Okay, it could also be 0, which is how we usually take it. So if we start at this, where the phase is pi by 2, so we go like this. So essentially we're starting from the top. Here we're starting from 0, and so this goes like a normal sinusoid wave. If we start with any random in between 0 and pi by 2, we start with any random, then at that point, whatever angle is getting formed, our wave starts from there. Okay, and they
Right.
are all parallel. If I didn't make all of these waves, all of them will come out to be parallel to each other. Okay, because my omega is the same, that is frequency is the same, and my
Yeah.
amplitude is also same.
Okay.
Okay, so when my amplitude and omega is the same, I will get waves which are essentially parallel to each other.
All right.
Okay, now we can quickly, and we can do this mentally also, we don't have to make the diagrams. Let's fix different things. So suppose I'm trying to figure out amplitude. If I fix the phase constant as well as the frequency, okay, and I'm taking, because the angular frequency is related to the frequency, if my angular frequency becomes constant, my frequency automatically becomes constant. Do you get this?
Yeah. I mean, yeah. I get it. I get it. Yes.
Right, omega is just equals to 2 pi into frequency. So if I say omega is 20, then I know there is a constant value, fixed value of the frequency as well. It's not going to change. If my omega is fixed, frequency is also fixed,
All right.
right? So in this expression, if I fix the omega and my phase constant and only change A, which is the amplitude, what's going to happen?
I mean, you'll be able to figure out the time then, because that's the only variable left.
No, I want you to tell me graphically what will I see. I want you to depict it graphically. What will you see?
Okay, so phi is constant, omega is constant. We are going to be tampering with amplitude.
Yes.
Yeah. So then basically how high or low the crest and troughs will be. That's the only thing.
Correct. So essentially, the nodes stay the same. The only thing changing is the amplitude. Okay, which could be high or low, whatever. But the nodes stay the same. Right? Very simple. Next, what if my amplitude and phase constant are same, but my phi changes?
Well, then there'll just be more crests and troughs in
Yes, then then we are essentially tampering with the frequency. So it will be either faster or slower. Okay, either way that we do. What happens if my omega and A are constant and my phi, which is the phase constant, change?
Yeah, so then you're just displacing the graph. So it starts at a different point.
Yes, that's what we did in the previous time. So essentially it starts at a different point. So it'll start from here or here, and in either case, okay, but they'll be parallel to each other.
Sorry. Yeah.
Right.
Yep.
So that's it. So this is essentially what we've covered today, is a very basic overview of simple harmonic motion. Okay, in the next time we'll actually go deeper, which is to understand the waves and understand the spring motion and all of those things. And we'll also do some questions as well. Okay, today it was more of theory. Okay.
Cool.
Did you understand it? Was it different from your normal classes so far?
It was definitely much काफी different था, yes. It's not just the class, like school class. I've missed a few classes. I'm not able to attend some, so I have gaps here and there. And but no, this I'm very comfortable with like it now. Yeah.
I'm glad. So our whole idea is to kind of make students think, and they can only think when they collaborate with us. Okay, so it shouldn't be a one-way class. We try to make it interactive. Now the students also need to participate, obviously. The more
Yes.
participative they are, the more fun it becomes. Okay, because we're able to look at different angles, sometimes even angles that we as teachers may not have thought of, right? Because when we prepare for our classes, it may slip out. So even then we go back and try to work out what can be improved and so on, right?
Right.
So let me know. I mean, let's do another class, which would be day after.
Sure. Okay.
And how are you liking the maths class? I know it was just one class so far.
Maths class was also good. It was much better than the classes in school, because I feel so like this is a more concentrated, right? It's 5 students, 6 students. I mean, in this case, it was just me. So I think you can help out students more and more effectively, because in our classes we have like in English, which is not either of these subjects, we have 73 students. It's crazy.
Yeah, makes sense here. The concentration is there as well. I mean, I understand the fewer number of students, but you should also start looking at it from how we are teaching differently, if we are teaching differently. Okay, so because no one teaches this much theory. I mean, if I continue at this pace, I was very slow today because I don't know at what level you were, so I was trying to go slow today. But if I continue at this pace, the theory itself will take us like 4 classes, 4 maybe 5 classes for just oscillation and waves.
Yeah.
Okay, which is probably not possible in our time frame, especially because we are starting quite late, right? So the theory becomes increasingly important, but at the same time, the theory is very important, because if you don't understand the theory, if you don't understand the importance of the words, again, like no one tells these things like how displacement is different. Okay, a lot of times I have gotten confused when I'm looking at different books, that is it the same displacement as we use in mechanics, right? Because if those concepts, that it's the same word but the meaning is different, and that little detail kind of shifts the whole perspective of doing any questions or even understanding the concept. Okay, so we try to be very minute about these things. Again, like I also acknowledge that students might not understand them, but that's why I'm telling you, so that you start seeing the nuances of it.
Yes.
Okay.
No, I've noticed this. Yeah, like in physics, it's a lot to do with declaring these are the quantities in use, this is the reference point. And I think those are the things where people make mistakes.
Totally. See, at the end of the day, okay, so I'll ask you a very simple question. What do you think science is?
I've actually thought about this. Like, I hear people saying science is like a quest. I've seen this on, like, you see it on TV sometimes. I don't have a TV anymore. Science is the quest for knowledge. the quest for truth. It's really not the quest for truth. It's just explaining phenomena which humans as a society experience, right? A theory does not have to be it does not need to be perfect. It needs to be able to predict and well map the phenomena in a certain way. That's my understanding of science.
Yeah, all of those things kind of fall into place, but I mean, those are like the second order of things. But at the basic, at the fundamental level, if you really look at science from a macroscopic way,
Mm.
it is just study of nature. Okay, when you are looking for truth, what are you looking for? You're essentially looking for truth in nature. Okay, you understand some phenomena. We see whatever, like a boat going up and down in water, and then we try to extrapolate that experience, that
Hmm.
happening of nature, onto whatever, onto diagrams, onto theory, onto whatever, right? So
Yes.
at the end of the day, science is just study of nature. And then the second thing is ki, okay, we might find the truth with it, we might simplify it, we might,
No,
get like these.
yeah, that's not what I meant in the sense. Yeah,
No, I mean, your thinking is
it's
also
just that I
good.
hear people saying that, and it's not. It's yeah. No, I'm just saying I'm thinking like you. It's just explaining phenomena and things we experience as human beings.
Yeah, yeah. So
That's what. Yeah, that's science. That's what science is. Yeah.
yeah, but a lot of people do not understand it. A lot of people kind of just go blindly in it. They think, hey, like it's just like some work that I have to do for school. A lot of students have that attitude, and we try to change that by showing them these nuances. Okay, because when you make them understand the details as to how a theory may be formed. I mean, I don't know how that particular scientist actually thought, but I can extrapolate now that, okay, if I want to make a new theory, this is how I would probably go about it. Okay. And when you go on that journey yourself, you kind of like you think of the same thing. Maybe the sinusoidal waves, maybe the SHM, whatever. You think of the same thing in very different 360 kind of a view. Okay, hey, okay, can we use this approach? Can we use that approach? And you might have also seen this with Atray Sir. I don't know if you're doing questions or not yet, but he also
We were doing
tries to,
questions.
and he does. Huh?
We were doing a bunch of questions. Yeah.
Yeah. So he also does a lot of questions from various different methods and things. Okay, depending
Hmm.
on what you've studied so far. So again, like I mean, that also comes from our father, but we try to kind of go into that and make you really think hard about a very specific small thing as well, because that's what kind of opens your mind. Okay, it's really fascinating. Like it will be very fascinating if you go that deep, but if not now, it's definitely going to help you later on. Okay,
Cool.
so perfect. Um, if you want, like if you have any other friends as well who would like to join, because we've just started the chapter, so I mean they
Hmm.
can also try it out. I mean, because you're also doing like trial classes for now, so ask your friends also to join in, and we'll keep it a small bunch. But the engagement level, as it increases, the fun in class also increases,
Yeah, I
right?
understand. Yes.
So because essentially if you don't discuss about physics, if it's just me talking about it, it becomes quite boring. Okay, and even for
Right.
me it becomes very passive.
Right. Yes.
Okay, so uh, ask your friends if they are also looking for someone to teach them physics, and are curious enough, not anyone and everyone, but like whom you think might be interested in learning from us properly,
Hmm.
and ask them and get us get them to join in the next class.
Cool. Okay.
Okay, perfect.
So I'll
Okay,
see
then
you day after
uh,
tomorrow.
day after, yes. Okay, you'll see Matrix tomorrow, and physics we'll do it day after tomorrow, same time.
Okay.
Correct?
Cool.
Okay,
Yeah, I'll
perfect.
see you then. Okay.
Bye,
Bye.
Harsh.